Accelerated electron. An electron, down here, with mass m and charge e, is accelerated from rest through a potential difference of magnitude v, due to this battery, between two long charge parallel plates. The electron then passes into a region of a uniform magnetic field that is directed into the page. On the diagram, sketch the electric field between the plates. Assume the plate separation is much less than the plate lengths. It doesn't look like that on the picture, but what we're really trying to say is the plates are like this, or even actually narrower. In terms of V and fundamental constants, this is a fairly standard AP problem. Determine the speed of the electron when it leaves the electric field. Describe the path of the electron in the magnetic field. Once again, in terms of V, B, and fundamental constants, determine the radius of the circle that the electron describes in the magnetic field. So we've just told you the shape. Oh well. If the magnetic field remains unchanged, what could be done to cause the electron to follow a straight path in the magnetic field? Part A, sketch the electric field. Because the plate separation is much less than the length of the plates, and of course the picture doesn't look like that, but you have to imagine the length of the plates being something like that, we will ignore the edge effects, and that will result in a uniform electric field in the direction of decreasing electric potential. So it goes from the positive plate over to the negative plate like that, and it's a uniform field because of the very tiny separation. In terms of V and fundamental constants, determine the speed of the electron when it leaves the electric field. So the electric field is like this. We showed that in part A. And of course an electron will accelerate opposite the electric field. So it's going to accelerate due to the electric field and leave here. And then it'll have a constant speed because the magnetic field will not change its speed. The electric field will perform work on the electron, where work is equal to the potential energy equals QV. The electron starts with zero energy, and what leaves the electric field that has a kinetic energy is calculated by the work-energy equation. So we're assuming once it gets here, it has no potential energy. All the energy is kinetic. And then the work here is changing the energy from here to a final kinetic energy here. So the work is the potential energy delivered by the field, which is QV. And since we're using the constants we have in this equation, the charge is E, it's an electron, and V, of course, is the voltage. So E capital V, and don't get the velocity V messed up with the voltage V. Okay, that's easy to do. Let's just erase all this again. And we have EV is 1/2 mass of the electron times V squared. Mass of the electron is certainly a fundamental constant. And our answer, the velocity, is a square root of 2e voltage over the mass of the electron. All of these were given or are fundamental constants, so we've met the requirements of the question. Describe the path of the electron in the magnetic field. It enters with the velocity v. We use the right-hand rule, and since the electron has a negative charge, the force will be opposite direction of your thumb. The force will always be perpendicular to the electron's velocity, which is a centripetal force, so that will result in circular motion until stopped by the plate. So let's see. When the electron comes in like this, you put your 4 fingers to the right and put your palm in the direction of into the page, because that's where the magnetic field is. That tells you that the force is like this for a positive charge. But this is an electron, so the force will be down. And then because we have a centripetal force here, the force is perpendicular to the displacement, we get this circular orbit. In terms of V, B, and fundamental constants, determine the radius of the circle that the electron describes in the magnetic field. We will use Newton's second law for circular motion, where the magnetic field force is equal to m electron v squared over r, where r will be the radius of the circle. The force is QVB, but in this case it's going to be EVB because it's an electron. Then we solve this equation for R, and we get MEV over EB. Now please do not stop here. You might say, hey, here's the answer. Frankly, that's what we had in the presentation. But the question asked to have answers in terms of fundamental constants and the given. We were not given the velocity. We were given voltage. Notice the difference there. So what you have to do to get full credit now is substitute in the value for velocity that you found in the previous one. Now, if you weren't able to do that on the AP exam, I would at least write this, obviously, because that's what you figured out, and then put a little sentence in saying, hey, I'm sorry, I didn't find the velocity, but I would use the velocity from part C. You may get a point, which every point counts on this exam. We put in the velocity, we simplify it so it looks pretty, and you don't even have to do that. This, of course, would be acceptable, and that's your answer for the radius. If the magnetic field remains unchanged, what could be done to cause the electron to follow a straight path in the magnetic field? So we want the electron to do this. Now you do the old free body diagram. We have a magnetic field force in the down direction. So we need an equal and opposite force, just like that. We could add an electric field, and that would then give us the net force of 0, assuming we balance the fields properly. Since the particle is an electron, the electric field should be directed in the down direction. And why is that? Because negative charges experience an electric force opposite the electric field direction. So the answer is a correctly balanced electric field in the down direction.